Good. Okay, so good morning and welcome to day 2. As Andrés promised yesterday, this day is all about variational inference. Thomas, Andrés, and I, we are going to spend the day with lots of slides, some exercises, and hopefully also some breaks if we find the time. This topic here is somewhat technical, so please ask questions as we move along. If there are things that I say that don't make sense, or when Thomas and Andrés come, if they do the same. We have a Slack also where TAs are monitoring. So if you don't want to speak out loud, you can ask your questions in the Slack, and then the TAs will help you there. Otherwise, please ask questions out loud too. Okay, so when we have this full day on variational inference, when we checked what other people do, they always start with some motivational examples of cool projects with nice pictures that really show you that this is the thing to be aware of. And the three of us, we have been part of a number of projects, but none of them produced cool pictures. So I've stolen pictures here from David Bly, who was also mentioned yesterday. He's one of the big guys in variational inference. And I don't really know much about these projects, but my promise to you is if you pay attention today, you will know about the core technology used in projects that produce nice pictures. So moving on, we are here at ProbAI to talk about probabilistic machine learning or probabilistic AI. And the reason for that is that building machine learning systems that are deployed in real life is hard. So when you are doing this as an academic like I am, you are having some fun, doing some math, downloading MNIST dataset, running, and if it doesn't work, it really is not that bad, because who cares? We already know how to classify those digits anyway. So it's kind of not really dangerous thing to do. But if you are going to deploy your system in real life, you are faced with lots of problems. So suddenly you have domain experts. They want to have input on how the modeling is done and what it means, and if you're actually catching what they know. The data is not as you expected it to be. It might be lots of missing values or erroneous values or difficult signal to noise ratios. Scalability is a problem. Robustness is a massive problem. One thing is the variation that you observe already in the training data. A completely different thing is variation that you didn't really anticipate when the model was trained, like auto-distribution examples, concept shifts, adversarial examples, and so on. Scalability, of course, yeah, did I mention that? And then trustworthiness is the new hot word to use in Europe, at least. So your system should be trustworthy, meaning that you can understand what it's doing and it can explain itself and it's robust and all that jazz. So trustworthiness is the keyword. And finally, if you're really unlucky, then you're also under regulations from governmental bodies, like you need to have transparency, explainability, not have biased solutions, and so forth. And the solution in this school is, of course, to build probabilistic models. So if you don't agree with that, then I guess you are at the wrong summer school, because that's what we do here. And yesterday and also today, we're going to be a little bit cooler than that as well. We are not only going to be probabilistic, but we're going to be Bayesians. And we have heard that a couple of times what it means, but I'll go quickly through it anyway. So the probabilistic part is that we are building a probabilistic model, P of X given theta, that tells us somehow how our data, how likely a data point is. So given parameters theta, I can tell you what is the probability of some observation that you come with. And being Bayesian then means that I'm recognizing that this theta is something that I'm uncertain about. I don't know what it is, so I'm going to put a distribution on it. And we start off with a prior distribution, which is modeling then what we know about theta before we get started, kind of. Often, or almost always, when we are Bayesians, we are kind of not discussing what this prior means. standard choice, it's a Gaussian, who cares? We can, or we will do that today as well. But this gives us at least the opportunity to make some sense about what we know. So yesterday, Andrés and Thomas talked about the mean temperature as a parameter at one of the thetas. So if you think about that, Andrés just moved from Spain, where the mean temperature, I guess, is like 25, maybe with standard deviation 5 or something. Every damn day he wakes up and it's sunny and 25 degrees. And then he moved to Copenhagen. So now his mean temperature is like 6, standard deviation 3, and that's in the summer. And then in the winter, it's not that nice. So understanding this then is going to help me to have information encoded in the model before I get going. So this is the point of the prior. And from now on, I'm always going to have a standard Gaussian anyway. But the point is, I could have used more time on doing stuff with that. And what is the important part of the prior for us here is that mechanically now, when we have this full distribution of our theta and data together, we can calculate the posterior of theta given data. So at any point in time when we have learned something through observing data, we can use this in a mathematically sound way to know what is now our best belief about what this parameter vector theta should be. And then, of course, downstream, we can use this for decision making. So I can here, for instance, calculate the probability of some new observation x prime given data by marginalizing out my uncertainty about the parameters theta. So again, being Bayesian now means that I am going to, at all times, retain this distribution over theta. I'm not going to use a point estimator. I'm going to have a distribution. Yesterday, Antonio said something like, we always use linear regression models because we only know about linear regression models. And that hurts because it's true. And we're going to use linear regression today. Lots and lots and lots of examples with linear regression. So setup is, we have this likelihood part. The probability of data given parameters theta is just a Gaussian with an offset W0, and the slope of the line is W1 times my x. And then for simplicity, I'm going to assume that this data noise is always known. So I'm not thinking about that as an uncertain quantity. I'm assuming that one to be known and fixed. So that means that in this case, the theta is simply my weights, W0, W1. And then I'm fitting a Gaussian, of course, on the prior distribution. And this then gives me the full linear regression model in the Bayesian way, as I'm now able to write out the joint of data and theta as the product of the prior and the likelihood term, where the likelihood term here is a product over all my examples. So that's the linear regression. Let's see where that brings us. So here is the result of a Bayesian approach to linear regression. So what we have on the right-hand side here is the posterior distribution of a theta given 5 observations from this generating process. So the offset is 1, the slope is 0.5, and I have some low variance noise on top of that. This gives me this posterior. So these are the contour plots for my parameter space after I've been learning. This is the most probable point in my posterior, so we call that the map, the most probable a posteriori point. The correct one is the black dot. My result is not that bad. So choosing to be Bayesian has its benefits, and that's what you're going to see now. So one thing would be to say, okay, I'm going to be like semi-Bayesian. I'm going to incorporate my prior. I'm using the point estimate that is the most probable thing from my posterior, and then see where that leads me. That would give me this red line over here, the map line. which is kind of okay, but I don't really know how good is it and how certain am I about its ability to help me in the future. So it's giving me a reasonable point estimate, but no model uncertainty. Whereas the Bayesian model, the full blue one, is then telling me something about the uncertainty through these contour plots. And the point of that is that I can now make these cool plots that Arthur showed yesterday, where I'm here sampling a number of possible mean lines from my posterior distribution, and then exploring kind of how certain I am about the result. So what we can see here is that I have some uncertainty about the offset, and I have a corresponding also uncertainty about the slope. And if we look back at the posterior, we can see that these two are, in fact, here negatively correlated. So if I am, say, sampling here and sampling a value of the intercept W0 that is higher than the mean at around 1, then I would accordingly sample a slope that is a little bit smaller than my mean, which is at 0.45 or whatever. So that's why when I'm starting out, say, high here, I'll typically end up on the low side over there. And if I'm starting on the low side here, I'm typically ending up on the high side over there. So this gives us these kind of crossing patterns. Cool. Then the posterior predictive. That's this part. So what I'm trying to do here is then to say, okay, I'm learning from these 5 data points. This gives me some estimate about the regression model. And now I want to predict what is the Y value if I'm sampling another X equals 0 points. So that will be something with mean around here and then some noise on top, right? And the noise level is known. So if I'm semi-Bayesian and using only the map, then this red thing here is the predictive distribution. So it's basically just degenerated at the mean and then adding the data noise. The blue one is the fully Bayesian, where I'm considering my uncertainty about where the mean is going, and therefore it's wider. So the question is then, which one do we like better? And since we are Bayesians, we like the blue one. And I'm going to give you a couple of reasons. So first, the actual mean is 1.5. And the red curve is kind of thinking that already 1.5 is unlikely. And I think even worse is that the data point that we have observed already at x equals 1 over there, which is like 1.55 maybe, is extremely unlikely under the map linear regression model. So basically, even though the map model has been told about our 5 data points, it's already refuting the existence of one of these 5 as part of something that is reasonable for this model to be learned in the first place, which is kind of sad. So the base model is better than at keeping track of its own uncertainty and then being able to use that downstream. So summary, Bayesian inference is all about being able to capture this posterior, this thing here, and utilizing that downstream. This is not magic. We can calculate it directly using a Bayes rule. So that's what's going on here. The problem, though, is this integral. We can solve that sometimes in very restrictive models. In particular, we can solve it for linear regression models, and that's why we like them so much. But for actual real models that are interesting, this typically doesn't work. So then we cannot solve this integral, therefore we cannot calculate this guy. And that's the problem that we are going to solve with variational approximations. So the goal today is to optimize an approximation. So we are going to invent a functional approximation that we will call Q. We want that one to be as close as possible to our true posterior, and we want this procedure to get to our approximation to be efficient computationally. We want to understand what it's trying to optimize, and we want it to be learned in a way that fits with how we are doing machine learning elsewhere. So we are not going to do Gibbs sampling and stuff that we saw yesterday evening. We are also not going to do degenerate solutions, but we are going to be Bayesian in an approximate way using optimization. So, any questions so far? No. Good. So this picture here is trying to explain what's going to go on throughout the day. On the left-hand side, this is our true posterior, P of theta given D. I don't know what that is. If I knew what it was, I didn't have to approximate it. So basically, I'm here inventing an example where I was making it a mixture Gaussian model, but typically you will not know what that is. However, what you do is you try to find a good approximation. And to do that, we need two things. First, we need what we call an approximation family. So these functions that are inside here, those are probability densities that I like, things that I can work with, things that are making sense for me computationally, and that are of a distributional family that also makes sense when it comes to approximating that guy. So like Gaussians or whatever. So this set is possibly infinite, and I'm using here lambdas to index that set. So you can think about if the set is all Gaussians, then lambda would be the parameters like mu and sigma. So this is a way to uniquely identify one of the members. And then we need to discuss how do we compare, say, this guy with that guy to find out if this is better than that one. And then we're going to use some kind of distance function here that measures the quality of the approximation. So having the set Q, having the way to define this thing here, and doing lots of pencil pushing, we are going to be defining how variational inference works. So slightly more formal, but just basically saying the same thing. We are approximating the posterior with Q. This Q here is always given data, but for simplicity, we don't bother to say Q of theta given D. It's always given D anyway. So it's just written as Q of theta. And then our task is, given this set of possible approximations, script Q, find the guy that works best. Then two decisions need to be made. What does it mean to work best? So how do we define this delta thing? And secondly, what is the set of possible approximations that we're going to choose from? So these are the two big questions now to define variational inference. Yes? No. So in this plot here, P is a mixture of Gaussians, and the Q is just univariate, or simple Gaussian. Yeah, sorry. Yes, good, thanks. So do ask questions. That's a good thing. We were discussing the distance function and what would we expect from a distance function. I did core math in my master's degree, and then I really liked real analysis. And there we have metric spaces and distances and stuff like that. And these distance functions, they are always assumed to have three important properties. First one is positivity. So if I have two objects, f and g, and I want to measure the distance between them, then positivity says that this distance is always non-negative, and it's zero if and only if f and g are the same object. So that seems reasonable. If not, then it's hard to talk about distances in the way that we understand them, like from real life. Symmetry is that the distance from f to g is the same as the distance from g to f. Also seems like a nice property to have. And then finally, the triangle inequality says that if you have these two objects, f and g, and then a new guy, h, then the distance from f to g cannot be shorter by being forced to go via h. if it was shorter to go via H, then you would just define the distance as the one that goes via H, right? Because it's going to be a meaningful distance anyway. So these three things, they are like crucial for defining distances. So we would like to have something that has these properties, but we don't. So for probability distributions, the default choice is to use the Kullback-Leibler divergence. So it's defined like this. The Kullback-Leibler from a distribution F to a distribution G, this one, is the integral of F times the logarithm of F divided by G. So if you think about that F being a distribution, it's the same as this thing here. The expectation over theta from the distribution F of log the fraction of these two PDFs by each other. Problem with the Kullback-Leibler is that it's not a proper distance measure. It has the positivity feature, but not symmetric and not over holding the triangle inequality either. So why do I mention all this? It's because it annoys me a lot. There are ways of doing, say, variational-like inference where you are using other distance measures. But today we are going to stick with the Kullback-Leibler, even though it does not have the symmetrical property and it's also not obeying the triangle inequality. Okay, so then we have decided our delta is going to be the Kullback-Leibler, but we are still not done. So we could do that in two ways. We could have the Kullback-Leibler from the approximation Q to the target P, or we could do it the other way around, from the target P to the approximation Q. And these are two different things because the Kullback-Leibler is annoyingly not symmetric. So I have here a couple of slides to try to convey the difference in what these two ways of measuring distance would then mean for how we optimize the Q. So remember, P is fixed, it's the target, and we are playing with Q to get it as close to P as possible, either using this definition of the distance or using that one. And then I have some helper cheat sheet things down there. Definition of entropy is minus the expectation under distribution F of log probability density. And then with that at hand, the Kullback-Leibler divergence from F to G can be written out as minus the expectation under F of log G of theta minus the entropy of F. So how can we now understand things? Well, this part is the one that's going to give us the important properties and differences between the information projection from Q to P and the moment projection from P to Q. And the way to think about this is that if this guy is 0, then that guy is going to be infinity unless F is 0 at the same point. So I'm cheating a bit here when I'm talking about points instead of small epsilon balls and stuff. So forgive me for that. All that dirty math is kind of skipped under the carpet. But the point is, we have to consider when is this 0 and what can we do with that guy to avoid the distance to become infinite, right? So let's look at our two candidates. This thing here, what do we do with Q to make this as small as possible? Well, point number one, of course, whenever we are looking at probability mass in Q, it's good that that guy is high, because then this thing here is going to be large and we get to subtract it. So we want Q to have probability mass wherever P has. Then the main point, if this guy is 0, then that guy must be 0 too. Otherwise, this thing here is going to explode in our faces. So if P is 0, Q must be 0. And then finally, we want the entropy to be high, and think about entropy more or less as similar to variance if you're not aware of that property from before. So that's the information projections. Moment projections is flipping P and Q in this part. Still, it's useful to choose a Q that's high in probability whenever P is. But now we need to think about what happens here. We can choose Q. So whenever P is larger than 0, so this part here is not 0 or contributing 0 in the integral, we need to make sure that Q is also positive, strictly positive. So whenever P is positive, Q must be positive. And here we are doing the entropy with respect to P, not with Q, and that's fixed. So entropy does not play a role in the moment projections. So basically, we have two different ways of thinking about that. The information projection is forcing us to make sure that Q is 0 whenever P is. Moment projection forces us to think about Q so that Q is always positive whenever P is positive. So slightly different. And it actually makes a large difference when it comes to applications. So again, here I have a target blue, which is a mixture of Gaussians with two modes. And I'm trying to find an approximation that is a Gaussian, a single Gaussian. And then my moment projection, the one going from P to Q, is the red line. And my information projection going from Q to P is the green line. So we can see they behave differently. The moment projection has larger variance. The information projection is focusing most of its mass on the main mode of the mixture. And if you zoom in on the left-hand side, we particularly see the difference clearly. So the moment projection is avoiding zeros. So it's trying to go high here. It can't go low here because this is positive, right? And then kind of has to have larger variance than P has. Whereas the information projection is trying to get low because it can't be positive over here when the target is actually very small. So two different behaviors. And then it's time to choose one or the other. And if you like moment projection better, then this is not your day, because variational inference is choosing information projections. So we are going to do Kullback library from Q to P. We will see why. It has a very nice interpretation when it comes to Bayesian machine learning, so that's nice. And we can also calculate it very efficiently if we are choosing our set of candidate functions in a clever way. The negative here is this zero forcing behavior. So what that actually means is that we are forcing the variance of Q to become smaller than the target. And therefore, we might underestimate the uncertainty that we have about Q when we are approximating it in this way. And to add insult to injury, the way that we are going to choose this set of candidates is going to make this problem even more prominent than it kind of has to be. Okay. So here comes one of the more tricky slides. It's not that bad, but there is some pencil pushing going on. I'll try to do it step by step. And the end result here is this elbow. So if you have read papers about probabilistic AI with the Bayesian flavor to it, then elbow is the crucial concept. And here it comes. So our starting point is this Kullback library divergence from Q to P. A problematic thing with that is we don't know what this thing is. If we knew what this posterior was, we didn't have to approximate it. So we are going to do some pencil pushing to get away from that. We don't want this thing to be part of our formula. So let's go. Starting here is just writing out what the Kullback library divergence between Q and P is defined as. It's the expectation under Q log Q divided by P. Then here I'm just multiplying by the marginal likelihood P of D, both above and below the fraction, basically. So far, so good, no problems here. Then this guy is a constant with respect to theta. So I can take it outside the expectation operator. And I do that first by recognizing that this is a log of a product. So when moving it out, it's the sum of logs. So this guy ends up there. And then I'm going to take the rest, this part, and just put it here, using that minus minus equals plus. So this thing is the same as that thing. Then keeping this one and just renaming that part as elbow, I'm done. So this thing here is now defined as L of Q, my elbow. And that's what we are going to play around with throughout the day. So elbow defined as this part minus the expectation under Q, log of Q divided by the full joint of theta and D now, which I'm just like restocking here by taking the minus sign inside the fraction. So what did we gain? Well, the main thing is we started off with this posterior that we were unable to calculate, and we ended up with this joint that we can calculate. So why can we calculate that one? It's because that's our model. We are modeling probability of data given theta and P of theta before we start, right? So this thing here is always available to us. So that's the elbow. Why do we like it so much? Well, it has some nice properties. Just like now, looking at this equation, Q-bar library equals marginal log likelihood minus elbow can be written like this, right? It's just restocking the terms. So the marginal likelihood is the elbow plus this Q-bar library divergence. And now this guy is constant with respect to the Q function that we are trying to optimize. It's just a number. We don't know what it is, but it is a single number. So that means minimizing this one, which is what we're trying to do, is the same as maximizing the elbow, right? Because they sum to a constant. So we cannot minimize the KL without also maximizing the elbow. So we are now able to work with the elbow instead of working with the Colbart ladder. And that then gave us this benefit that we are getting away from working with the posterior and rather working on the joints. And then I said that the elbow has a nice interpretation, and that comes from this guy being non-negative. So that means this is a lower bound for that. So basically, we are trying to optimize a lower bound for our marginal likelihood of the data. And that's what we are going to do. We are looking for an approximation Q that maximizes this elbow thing. Make sense? Makes sense. Summary of summary. We started out with this Colbart library thing. We are not liking that because we don't know the posterior over theta. So we rather invented this elbow, and now we know that maximizing elbow is the same as minimizing Colbart library. So we are basically set, and we can go on to something more fancy. Questions? Yep. Okay, so let's go back to our linear regression example like this. So this is basically, oops, fuck. Wrong button, like that, yes. So when I'm building my model, I'm building a likelihood part, which basically tells me how each data point comes into play, given the parameters. And then here I'm assuming that all my data points are independent and identically distributed given the model. So this is P of D given theta. And then multiplying that by P of theta, which is my prior, I have it. So for any configuration of a set of thetas and all the data, I can just calculate that number. Good, yeah. Other questions? For the linear regression, yes. For me today, at least, it is. So sometimes we have models where we cannot calculate this, but that's not today. Right? Yeah. Good. Okay, so we have the distance measure, the delta. We are happy with that because we have been playing around with it and found that we can actually minimize that by looking at the elbow, maximizing the elbow instead. So now we need to find this set Q, the set of candidate functions. And the most popular way of doing that is by using something called mean field. And that's what we are going to do as well. And basically what that says is that in the posterior approximation, this thing here, we are going to assume that each dimension is an independent variable of all the others. So the joint over theta in the approximation is just a product of the marginals. Sounds quite restrictive, but you will get to see some tricks later. Not today, but when you talk about normalizing flows, for instance, you will see cool stuff that still works and give amazing results, even though this basic mean field assumption seems really odd. It's really helpful for the calculations, and I guess that's why we started off with it. And later on, you will get to see, as I said, more cool stuff that helps us accept that this assumption is nice to have. For now, I have a sanity check example. So what I've done here is copy in again that picture here of the linear regression result. So you remember the linear regression, we have our observation y is a linear combination of two unknown parameters w0 and w1 times the x, and then with the fixed data noise and fairly vague priors in this example. Then this is the full libation solution. Here is the variational result. So if you look first here, we have the contour plot here for the in blue for the full libation solution, showing this negative correlation that I talked about. If you start off with a too small or smaller than mean offset, you will typically have a larger than mean slope. That's the negative correlation here. The green stuff is the variational approximation. It has the mean field assumptions, so these two axes are now independent, and that leads to results like this. So we can see here that the structure is more like, say, a cone or a fan. We don't have these crossing patterns that we have for the full libation one. We have like whatever happens here is not going to tell us something about the slope. They are independent. And that's just what we assume. So live with it, kind of. When it comes to downstream behavior, in particular here, trying to say something about the distribution for y, given that I'm going to observe now a new x equals 1 example, the posterior predictive for the variational and the Bayesian fit fairly well. So it does not have to have disastrous results downstream, even though we can see we can see quite a difference between the posterior approximation, the green thing, and the actual posterior, the blue thing, when we are only looking at the joint distribution here of the theta. Yes, those are the only two parameters I have, because the data noise is observed or known. You sound unhappy. Yeah, so in this example, I have the Bayesian solution, right? So it's a naive example to run with, but I just wanted to be able to plot the actual solution so that I can compare with my approximation and show you the effect of the mean field like this. Oh, yep. So there are, say, intermediate solutions. If my data noise had not been known, I could have then said that, okay, I'm going to make an approximation where I have correlation between my weights, but not between the weights and the sigma. So I can have a generalized mean field, as it's called, and you will see an example of that later. And then, of course, when I generalize enough, I have the full Bayesian thing back. So then I'm out of luck if I can't do that analytically. Good. Move on. Yeah. So setup. We are going now to try to maximize this elbow thing. And that's the, say, next goal. So we have observed this data. We are able to calculate the full joint, the probability distribution over theta and d. We are going to use elbow as our objective when we are finding an optimal Q. And we're going to assume that this Q factorizes. So we are assuming the mean field. Then we are going to posit or just like define distributional families for each component in the approximation. So each Q, now I'm using Qj here to talk about component or dimension number j in theta. So each of these has a known distributional family, and it's the parameters that I'm going to optimize over. So I need to find those parameters that I'm calling here lambda j. So j is then the dimension that we're talking about. So the algorithm that I'll run is that I'm going to keep going where I'm first running over all the dimension of theta, then optimizing the parameterization of dimension j based on the data that I have and my current solution for all the other parameters in the full distribution over Q. And then when I've done that for all dimensions, I'm going to calculate my new elbow, check if it's a significant improvement, and if it is, I'll keep going. So that's kind of an, say, an EM-like algorithm, if you're old enough to remember EM, where we are basically assuming that the distributions that we have, except j, are useful for finding the distribution for theta j, and then we are moving. Yep. They are Gaussians, so that's going to be assumed, and we will see that when we solve this, we have an analytic form for what it needs to look like. So knowing that, it's helpful to choose Gaussians. Later on, we will not have to do that, and we can have represented by something else. Was this when we planned to have a break, was it? Okay. Do we have time for that? 5 minutes break? Okay, so we continue. If I'm going too fast, then let me know. And if you think I'm going too slowly, that would be nice, because I think we are behind schedule already. So let me know then as well. Recap, variational inference is about finding a distributional approximation to an unknown posterior distribution over theta. So we have this P of theta given D. We don't know what it is, but we know that if we can find the approximation that has the highest elbow, then that is also the one that is closest to the unknown posterior. So we have, the setup is, as I showed you before, we have this approximation family Q. We have decided that that should be mean field. I had a question in the break also about distributional families to be chosen. So I go with Gaussians or whatever. And we will see that quite soon. So having this family, I'm going to assume that I can index that using parameters. So we have this lambda, lambda 1, lambda 2, lambda 3, lambda 4. Those are 4 different or distinct distributions inside that family. And then our goal is basically to find the lambda that is maximizing the elbow. And that's also then the lambda that minimizes the KL divergence from Q, the approximation, to the unknown targets, P of theta given D. And this slide here is tedious, so that's why we gave you the break before showing it. Hope you used the break wisely. Because what we're going to do now is basically find out how these pieces fit together and then how we are going to choose these lambda parameters. So starting from the top, this is the elbow. That's the guy that we want to maximize. And we're going to maximize it with respect to Q. Our assumption is that Q factorizes. So when we are picking out one dimension J, the joint Q of theta can be written as the product of that marginal over theta J times whatever is left. And what we're going to do now is to keep this part fixed and try to optimize that guy. And then we're going to do that for each dimension, and then we feel that we have done some proper work. So that's the plan. And then we are going to utilize some tricks as we move along, and I have tried to highlight those tricks with yellow so that you can follow. So what I've done here first is just to write out what the elbow is. It's the log of that fraction, which is just the log of the first guy minus the second guy. The expectation is with respect to Q. So that is the full distribution over all thetas. And what's happening from here to here is basically that I'm just like writing out the expectation over the full joint is the expectation with respect to the dimension that I'm interested in, and then the expectation with respect to the others. I can do that because of the mean field. I don't have to think about what is going on at all. So that gives me this, or this rather. And now we're going to attack these two terms one by one, starting with this guy. So that thing looks nasty. So we are just going to use notation to make it less damning by calling it something else. So what we do is to say that, okay, let's define this function here, fj tilde, so that the log of that is this thing. So basically, I can write log fj tilde here instead, right? That's just a notational thing. And then I'm going to do a little bit more and then say that, okay, it's difficult to say tilde in English all the time. So I'll invent something that doesn't have that. And it's just the normalized version. So this thing here follows from that guy by just ensuring that it integrates to 1. So that means if I'm putting those parts together, that this expectation that I wanted to get rid of is that guy plus a constant. Okay? Using here that the log of a fraction is a log of the first term minus the second term, and then C1 here is going to be minus log of that. So I can now put this thing up there. Boom. Then the second term, I'm going to do something with this as well. What I'm going to do is first to write out that under the mean field, this joint is the product of dimension j times the joint of the other dimensions. And then utilize that the log of a product is the sum of the logs. So this gives me that. And then what can we do? Well, we have that part already explained. Then from here to here, this term is not depending on the distribution of those other guys. So I'm just dropping that expectation. This term does not depend on the expectation over qj because it's constant with respect to qj. So I'm dropping that expectation here. And now, finally, this thing here is a constant with respect to the distribution over dimension j. So it's not part of the optimization I'm doing now. I'm just calling that a constant too. So that's going to be C2. Okay? So it's just pencil pushing, no magic going on at all. And then I'm just rephrasing that up there. And now we're actually getting somewhere. So recall now that this guy was invented so that it integrates to 1. So I'm now going to call that a probability distribution. It has to be positive because it was defined so that the log of the thing was a real number. So this is positive, integrates to 1. Let's assume it's a probability distribution. Then writing this thing here up is just now the Kullback library from QJ to this FJ thing. Okay, I can do that. It's not wrong. So then I do it. This gives me that result. So what do we have? Well, the elbow with respect to Q, when we are seeing it as a function of Qj and constant thing there, is a constant C minus the Kullback library from Qj to this Fj thing. This is what we want to maximize. How do we maximize that? Well, constant is constant, so we're not going to do anything with this one. Then we have minus the Kullback library. Kullback library is non-negative, so it's nice if it's 0. How do we get it to be 0? Well, thank God the Kullback library is observing the positivity constraint, meaning that these two must be identical if the Kullback library is to be 0. So that means, again, this guy must be chosen like that guy. Tracing back, we know what Fj needs to be. It was this time expectation that was hard to understand what meant. And basically, that's the result. So if I'm trying to optimize elbow with respect to dimension j on my approximation q of theta, then I have to choose it like this. So what does that mean? Well, I'm going to write out, or Thomas and Andrés are going to write out when they get to show some slides, what this thing here is for the model. Here we will have a function with respect to thetas. Then we are going to take the expectation of that equation with respect to all the other parameters than the one that we are interested in. That's going to give us a distribution definition. That's the one that we will use for theta j. So that's kind of, I think, cool. What we had to do was only to assume that we have the mean field, and we had to do like a coordinate descent thing. We are assuming that all the coordinates except number j is fixed, and then optimize with respect to only the qj. And now we know how to do that optimization for qj. And then we're going to keep on over all the dimensions. When we've done that, we will calculate the elbow, see if we have improved a lot. If we have, keep going. So I showed you this already. The setup is that we want to optimize the parameters, and then we cheekily wrote that we somehow choose the parameters so that they are cleverly defined. Now we actually know how to do that definition. So we're going to choose the parameters so that this works. That's the whole thing. And this is called CAVI, Coordinate Ascent Variational Inference. And that's the classic way of doing variational. Yes? I'm not sure if I got that. So what we are doing is that we are saying here, if we keep the others fixed, then this is the optimal thing to do for dimension j. So if you start with just inventing random numbers for all except dimension number 1, then you're saying, okay, dimension 1 is the one I'm looking at. The best I can do given the others is to fix parameters like this. And then you're doing number 2. Then at least number 1 is better chosen than it was before, right? So then number 2 is going to get some better behavior because of that. And then it's going to, let me see if, yeah, I have a video coming soon, so we will see how it works. Other questions? No, so just to conclude this, what we have now is a procedure where we dimension by dimension know how to update our Q distribution so that it is approaching the posterior. And we are able to do that even though we do not know what the posterior is, which is kind of magic in my eyes. Yeah. That's for Thomas to answer. There is some mathematical theory here with what's this Banach theorem, compression theorem. There is math here. This came out like in around early 2000s, and then at that time I actually read up on it, and it works, but I don't remember the details anymore. Oh yeah, yes. In practice, you will monitor your elbow, and then you will see that that kind of grows and then stops growing and pans out, and then you're done. No. So this is always increasing until it converges. And then how to what level it converges depends on your assumptions and the mean field and all that, of course. But I thought you meant mathematically. Why is this algorithm converging? Sorry. Yeah. Yeah, first here and then there. Yeah, yes, go. Mm. Yeah, so if we think about, say that Q is a multivariate Gaussian, then basically what you're doing is that you are assuming that the covariance matrix is diagonal. So when you're picking each element on the diagonal, you're looking at the other diagonal elements, but you're not looking at what's outside the diagonal of the covariance matrix. So it makes sense. Sorry, I had the guy back there first. Yeah. Here it always converges. So this is well defined. So there are no local optima here. So convex, yeah. Hmm? What you don't have any correlation, but the say the width of or the variance locally can depend on the level of the variances. So the diagonal elements can communicate kind of.
So you have to think like, I mean, when you say that the uncertainty of one parameter is measured through, for example, under the Gaussian, you have a Gaussian mean field, the uncertainty of one parameter is going to be reflected in the variance of this Gaussian, okay? And then the variance of this Gaussian will affect when the updating equations of the other parameters of the another Gaussian, okay? So there can be a communication in that way, even though you will always have a mean field. So you will have a posterior approximated by a bunch of independent random variables. Okay.
I'll show this on the video coming up. So what we have here now is a video of Kali running, or you will get that soon at least. So as always, the blue thing is our correct posterior, so the one that we are trying to approximate. Usually we won't have it, so you can't be making these nice videos, but here it's a linear regression example again. So I have it, and that's why we chose that in the first place. The green thing is my variational. And I'm starting off here with Q being equal to the prior. So that means the mean is that dot down there that you can barely see. And the variance here is huge, I think 100. And so what I'm going to do now is do KV. So that means I'm first optimizing along this axis, the distribution for that guy. Then I'm doing the distribution for that guy, and then back again to the offset, then the slope, offset, slope, boom, boom, boom. So basically, I'm going to get a movement like going like this up here. And the first thing that happens is that given the high variance over here, how should I select the mean for the offset and its variance? And what's going to happen is that you can think of this guy here as having some probability mass down there too. So we're going to move the mean over there. And given the large variance over there, it's going to reduce the variance in this direction, and then they are going to like talk together and converge. So you can see that happening here. So this is the KV at work, and you can see it's making large movements in the beginning, resulting in high benefits in elbow. And then as we are moving along, there is less and less to gain for each iteration of the algorithm. And then you can just like turn off whenever you don't want to wait any longer. Questions about this? We will see lots of examples of this running now, I think, in detail. Oh, okay. Who's up? One of you guys. Yeah. Yes, so this is this generalized mean field where I can choose subsets of variables that I want to communicate and be correlated in the posterior approximation, and that is something that we will see an example of later on. So then you need to think back to the definition of the KL, as you say, and we are afraid to put mass on areas where it's very close to zero. So variance is very quickly being reduced, and it's trying to put the mean like where there is probability mass in the posterior, and you are only allowed to move along the x-axis now, right? And then it's moving towards whatever 1.3 or something, and then reducing the variance a lot to not put probability mass outside where it can. Yes, probably, yeah.
Okay, can you hear me? Yes.
Okay, go. So for this to be analytically attractable, you do exponential family stuff. Later, we will do gradient-based stuff where we are not analytically solving the elbow problem, and then we are relieved from that assumption. But for now, the analytic part requires exponential family. We try to hide those mathematical details away from you, but you're too clever for us. Good, thanks. So you don't know how, you don't understand how we can actually approximate something that we don't know what is. And that's the magic of the whole thing, isn't it? But
maybe can I mean, the question is that we have the join over theta and d, okay? Perfect. And there are two ways to compute this quantity. You can do it that way. Okay. That way you can compute it, as Helge saw before. Okay. And then you have this other way to express the same quantity. Okay. And this way involves the posterior. Okay. That's the trick. It's like you have something like that, and then you move it to something like that. Which is the problem of this quantity? The problem of this quantity is that is expressed in that way. And which is the problem of computing the posteriors, that we cannot, is this constant down here, that computing this constant requires to compute an integral. Then when we have a highly multidimensional model, this integral is not tractable, okay? So you cannot solve a multidimensional integral, you don't know how to solve it. It's really hard. Because this is really hard to compute, you can't compute this guy, okay? But, you know, playing around with this equality is how you achieve to the elbow, and then you transform the problem of computing this posterior in expressing this joint distribution, okay? Kind of intuitive reason. The problem is this guy. I cannot compute this guy, then I cannot compute this guy. In consequence, you know, I have to play around, and at the end I'm trying to re-express everything with this equality, as Helge saw. Okay, perfect. Okay. So, well, the question is that you have seen like an abstract way of thinking about Bayesian, which is coordinate ascent variational inference. Okay, I'm going to show you a kind of quick overview. How does it really mean to apply this general algorithm to a very specific model? Okay, so let's go for I would say one of the simplest probabilistic models that we can count, which is a Gaussian model. So X is a random variable. Okay, actually I have a bunch of random variables representing a bunch of observations, my data set. Perfect. Then X is going to be normally distributed. So the distribution of Xi is going to be normal distribution. And then the normal distribution is parameterized by the mean, mu, and the standard deviation, sorry, the variance, which is going to be expressed as 1 over gamma. Why? Because gamma is going to represent the precision. So instead of speaking, instead of speaking in terms of mean and variance, I'm going to speak in terms of mean and precision. So when we are defining a Gaussian distribution, a normal distribution is just the same. Instead of going from mean variance, we express it in terms of mean and precision. Perfect, which is 1 over the variance. Okay. The question is, I then have again, you know, the probability of D given theta. So which is theta in this case? Mu and gamma, the mean and the precision of my normal distribution. As you can see, okay, these are the observations, which represents my data, and these are the parameters, which are unknown. Perfect. So when I have these quantities unknown, what I do? I define a distribution over these unknown quantities. Okay. So for mu, which is the mean of my Gaussian, I'm going to define a normal distribution, and for gamma, which is the precision of my Gaussian, I'm going to treat it as a gamma random variable. Perfect. Actually, you may ask, why are you choosing these two guys? Because it's important to choose these two guys, because then when deriving the variational updating equations, I'm going to have a closed form, something that can be, you know, a bit of pencil pushing, and then you arrive to a closed form, something I can implement. Okay, nice. The question is, I have this PD of theta. Okay, then just remember, okay, I'm going to take it that way. Okay, I'm not going to take that way. Okay, I'm going to take that way. Perfect. And this is what I do here. Okay, and then I'm going to also apply the logarithm. Perfect. So, you know, so there are a lot of Greek letters here. Perfect. But the idea is, this is the log of the probability of D given my unknown quantities, my parameters, theta. These are guys that defines my prior over my thetas. Okay. And then, you know, that's expressed as like the log likelihood over the data plus the components representing the prior. Perfect. Okay, that's our log of the prior, and this is the log of the data. Okay, when I expand it. Okay. Important thing, I need to compute the posterior. Okay, so I don't know how to compute the true posterior, so I'm going to go for a variational solution, and then I'm going to define a Q over theta. But how many thetas do I have? I have 2 thetas, okay? One for the mean and another for the precision. I'm going to do mean field. What does it mean? Like my Q over my theta is going to factorize Q over mu, Q over gamma, 1Q for each of my unknown parameters. Perfect? Okay, nice. And then remember, what I'm trying to do is I'm going to try to find which are these two Qs, okay, that multiply together, defines a joint distribution that multiply together are as close as possible to the posterior, to the true posterior. Okay, something I cannot compute. Okay, well, in this case I can, but we are going to assume that we cannot. Okay, perfect. And then I'm going to solve this minimization problem. In order to solve this minimization problem, I'm going to maximize the elbow. Perfect. And to maximize the elbow, I'm going to use this coordinate updating equation. Okay, coordinate updating equation. I maximize the elbow. And then I solve this minimization problem. Perfect. Yes. Remember, when we speak about variational distributions, this guy is going to be a normal. And at the end, this Q is going to be defined by the parameters of this normal distribution. Q of mu is a normal distribution. Perfect. I need to find the normal distribution which is as close as possible to the true posterior. Okay. So in order to define this normal distribution, I'm going to use variational parameters. Two variational parameters defining the normal distribution for this guy, and another two variational parameters defining the gamma distribution for this guy. Perfect. Actually, if you realize, I'm using here normal, same as the prior, gamma, same as the prior. Perfect. Okay. And then my problem is going to be to find the value for this guy, the value for this guy, the value for this guy, and the value for this guy. Okay. So I'm going to have 4 numbers. And then I need to find 4 numbers that define a Q distribution that make us this Q as close as possible to the true posterior distribution. Perfect. Yes. Say again, sorry. Yes, so exactly. So the question is, and this is something that we haven't discussed here. The question is like, in this coordinate ascent variational inference, okay, what we really want to is to find closed form updating equations. In order to have closed form updating equations, we have to choose, we have a specific choices for the distribution of this guy and this guy, the variation approximation, and also for this guy and this guy. Okay, there has to satisfy what is known like conjugate exponential family. Perfect. Okay, this should be conjugate exponential, conjugate distribution. Perfect. That's the restriction. After lunch, we will see how we can get rid of this restriction. Perfect. But there will be another payoff. Okay, we will speak about that. So let me go. So the question is, I need to find the Q over mu, one of my unknowns. Okay, the Q over mu depends of these 2 variational parameters. Okay, how do I find these 2 variational parameters? Well, I have what Helge showed you, the variational updating equation, and means that the log Q, the log of my variational approximation equals the expectation with respect to the rest with the others variational parameters. In that case, I have 2. So the log of Q over mu depends of the expectation with the other, which is the Q of gamma. Perfect. This is the other variational parameter. And then this expectation with the other variational parameters of the log of the joint. Perfect. Okay. So how do you proceed in order to derive the variational updating equation? Because at the end, so what we have here, okay, when we treat this guy as a normal distribution, is this expression over here. Okay, so this is the log of a normal density. The normal density depends of this nu Q and this tau Q, which appears here and here. Okay. So the idea when deriving this variational updating equation is like you should express that in terms of nu squared and nu. So the idea is like any normal distribution any normal distribution parameterized by these two guys can be expressed in that way. Some number that multiplies mu squared plus some numbers that multiply mu plus some constant that we don't care about. Perfect? Yes. The question is, if you start to expand this guy, you expand this guy, then you take, I will give you the details quickly, but you will end up having, after some expanding pencil pushing grouping terms, you will arrive to this equation over here. And then when you match, then you realize that, I have some number multiplying mu squared. Okay. I have some number multiplying mu squared. Okay, so this guy should be tau q. And then I have another number multiplying mu. And then, okay, this guy should be the multiplication of these two guys. Okay, so if I do a bit of math, then I realize like tau q, okay, tau q is going to be equal to this guy. And mu q is going to be equal, okay, to this. Perfect. Okay. One important point. Can you see here? This guy, which is going to define, which is the variational of mu, this guy, which defines which is the variational of mu, depends on the expectation with respect to the another variational parameter. Okay. So this is because when I update tau q, okay, which is the precision of my variational posterior, is going to be impacted by the current solution, the current variational solution for your gamma distribution. Perfect. And this is the change. So I update mu, okay, and then you will see that I will have a different variational data equation for q of gamma, okay, and then there is when we have this, okay, yes. I think this is a technical question that we can discuss together. Okay, so because I think we cannot prove that. Okay, that's my impression. Okay, and I think you have to think in terms of the exponential family, but it's a kind of technical question. I will be happy to discuss it with you. Okay, any other question? Yes. Exactly. Yes, Missy. Tau here parameterize the variational of mu. The q of mu is a normal distribution. Then tau defines the precision of my variational distribution. Tau q. Okay, you mean this one? Okay, perfect. Okay, sorry, I thought this is the precision of your prior over mu. Perfect. Okay. So at the end, your variational solution is going to be impacted by the variational solution over the other parameters plus the prior. Okay, and that also happens here. The variation over the other parameters. Okay, and well, in that case, it doesn't appear the prior. Okay, directly. Okay, but it's involved. Perfect. Okay. So, given the time that we have, the idea or the only missing part here is how we go from this part to this other part. Okay, and this is what you have here. Okay, and I think I'm going to skip this part. Okay. So I think it's nice. So it's very well detailed. Okay. I think if you use it, with the slides, then you start to reproduce everything. Everything is well detailed here. And at the end, I'm going to do it quickly. It's like you exploit these kind of equalities, and then you express it like that way. It's like the log of the expectation of the log of the data plus the prior. Okay. Now, when you have the log, the log density of an X given my parameters, because this guy is a Gaussian, then I have this density. This guy is a Gaussian, I have another density. I made that. I made a bit of expansion. I made a bit of regrouping, and then I arrive here. Perfect. So, okay, this is how it's done. Just pencil pushing, okay, patient, be careful, and then you derive the updating equation. Okay. Perfect. The question is, I now have this Q over mu. I have these two variational parameters that define my Q over mu. Then I fix them. These two variational parameters define a distribution over mu, the variational over mu. Having this guy, I'm going to compute, I'm going to update the distribution over gamma. Okay? How do I do it? Exactly the same way. Perfect. But now we are working with a gamma distribution. Then we have to consider the density of the gamma. And at the end, what I have is this updating equation. So the density over the gamma distribution is going to be defined by two parameters, alpha q and beta q. And then alpha q is depends a kind of constant value, okay, which depends on the sample size and the prior. And the beta q is this expression that involves the computation over the posterior over the mean, the variational posterior over the mu parameter. Okay. Then update the q over gamma, given the q over gamma, then I update the q over mu, then I update the q over gamma, then I update the q over mu, and every time I increase my elbow until convergence. Perfect. Okay, any question? Okay. I know this is a bit technical, but the idea is like you get really an impression of what does involve. Okay. Perfect. The question is like, even the elbow itself can be computed, okay, in the same way, okay, as then when you expand it, and then you can compute it in closed form. You compute the elbow in closed form, okay, something that only happens in this specific case when you have a specific distributional families. But the nice thing is, every time that you make this variational updating equation, the elbow monotonically increase. And this is something quite nice because, I mean, you may make an error making this derivation. So you make an error, your elbow will do not monotonically increase, and then you know that you have an error because it has to monotonically increase after each variational updating equation. Perfect. Then it increased, and when it plateaus, you say, okay, I have reached the solution, I can stop, and then I have two Qs, one Q for mu, one Q for gamma, and then these two Qs define the approximation of my posterior distribution. Perfect. Okay. Any question? Well, the idea is like we have, let me see. Well, we have prepared this student simple model notebook, but I think it's better that we, let me see. Yes. That we open the solution simple model. So let's go for the solution, directly to the solution. Perfect. And then we are going to show you how it really translates to a kind of, real exercise. So in this notebook, we have coded this variational updating equation for this Gaussian model. Perfect. You can see how they are coded in real code, which is the effect that it has in the monoidal increase of the elbow. Okay. And then I will start to run it for you here. So the first thing that we do here is like we fix the prior. The parameters defining our prior over mu and gamma. Okay. Then we generate some random data. Perfect. Then we have some helper function to make the plots, another function to compute the elbow. Okay. And then these are the variational updating equations, okay, that we have shown you before. And these are the variational updating equations that are coded in this piece of code down here. Yes. These are the variational parameters, alpha q, beta q, mu q, tau q. These two guys define the variational posterior over gamma, and these two guys define the variational posterior over mu. Perfect. The idea is like we have a loop, and then within each iteration of the loop, I compute alpha, beta according to to the variational updating equations, realize that this alpha q, beta q that defines the variational posterior over gamma depends of the mu q, okay, that defines the variational posterior over mu. And when computing the tau q, mu q, which define the variational posterior over mu, you know, we use something that depends of the variational posterior over gamma. Okay. And then we run this after each variational updating equation, we compute the elbow. And then what we can see here is clearly a monotonical increase of the elbow. And then the parameters converge. Okay. And if this was our prior, you know, and sorry, and I don't know why it's not plotting this. Wow. Okay. Anyway, wow. Why it's not showing this density? No idea. Anyway. So the question is, this is, wow. I don't know, when you run it, disappear. Oh my God. Anyway, I think you will probably be able to plot. Okay, the plots, I don't know what's up. Anyway, and then you converge, and then you have these two Qs that combine give you this approximation, which is a bivariate distribution, which approximates the true posterior distribution. Perfect. So the idea is like we are going to have a break now. Well, exactly. Yeah, sorry. So please spend a few minutes playing around with this notebook. Modify the prior, you know, have a look, convince yourself, okay? And then after that, we will have 5 minutes break, okay? 5-10 minutes break. Perfect, and then we will continue. Sorry? Okay, so let's spend like 3-4 minutes on the exercise, and then we will tell you how much do we have for the break. Okay, we need to accommodate the time. Okay. So so you have any questions? So we will be working around, and we can just raise your hand, and then we will go to your place and answer any question that you have. Perfect.
Okay, so welcome back again. It's time to get started. We have so this last session here before lunch is going to last until 11:45, so that we have about 15 minutes for photo session afterwards. And we are going to spend a bit of time now where I'm going to introduce a bit of show some slides, and then we'll move on to notebooks again. So, okay, maybe we should just wait until everybody's in here. Okay, so the nice part for me is that now Andrés and Helge have been dragging you through all the math, and then I was now given the task of making it much more enjoyable with focusing a bit more on notebooks and some graphics and playing around and all that. But first, we are going to dive a bit more into Bayesian linear regression, which you have seen a couple of times now, but which we are just going to take a small iteration over again and see in order to give you the basis for analyzing a data set that you're going to play around with in the exercises in just a few minutes. So the data set that we'll be using is called the ruggedness data sets. It's a data set that has also quite extensively been explored in some existing Pyro tutorials, and we've borrowed some of the concepts from these tutorials. So the data set consists of information from 170 countries that has been divided into African and African nations. And this is sort of what you see in the plots up here. To the right, you have the African nations. To the left is the non-African nations. And then for each of the nations, there is information about the so-called ruggedness index that says something about how rugged the terrain is in this particular country. And then we also have information about the GDP. In this case here, on the y-axis, we plot the log of the GDP. And what one can do is to try to analyze this data set here using standard linear regression. And if one does that, then we can do the exercise for you by dividing up the data set into two parts for the African and non-African nations. And then you get sort of the lines that you've drawn on the slide here. And sort of one of the things that stand out is that the slope of the two lines points in opposite directions. So for non-African nations, you have a negative slope, and for African nations, you have a positive slope. And the question is then, are these conclusions really supported by the data, or at least to what extent are the conclusions supported about in the data? And not surprisingly, we are going to try to analyze, investigate this question a bit more, but now taking on our Bayesian hat and using the Bayesian toolbox for doing that. Good. And the particular model that we'll be using is sort of our linear regression model, now packed within a Bayesian setting. And this is what we've tried to illustrate up here. Again, using plate notation, we have the response variable yi, which for our particular data set here will be the log of the GDP. Xi will be the ruggedness index for a particular country. We have W, which would correspond to the slope, and we have B for the bias term, the intercept term is also represented up there. And these are our two uncertain quantities, and we give them prior distributions, so a prior normal distributions over W, the slope, and over B. And in this case here, the model is specified sort of in generally for Bayesian linear regression model, where we have we assume that the data set, the predictor variables, has a size of M. So that's why that you can see that we have this capital M indexes on, for instance, the identity matrix for the prior distribution over W to indicate that this is sort of a general Bayesian linear regression model. But for our particular data set that we'll be working with, M in this case here will just be equal to 1. We also have, in this case here, the precision associated with the Y variable here. So the data uncertainty, that's assumed to be a fixed quantity. So we don't have any uncertainty over that. So that's just to make this exercise here a bit easier. Again, we can define this graphical models, define the joint distribution. You can take with the likelihood term and multiply that together with the two prior terms, and we get the joint. And in order to find the updating rules, we'll be looking at the log of the joint. So when you take the log of the product, then you have the sum of the logs. And this is basically what Andrés and Helge were pestering you with earlier today. And we can divide it up further by decomposing it according to the factorization of the model. And we will also, in this case here, assume a full mean field model. So again, meaning that our model, our variational distribution factorizes over the individual components in the model. And as I mentioned before, so this here is for a general Bayesian linear regression model. In our data set, we only have one predictor variable, so M here in this case would be 1. So you have a variational distribution over the bias term, and you have a variational distribution for the slope. And if we start to do all the pencil pushing that you've seen a couple of times by now, we can derive the updating equations for, in this case here, the slope. And again, it's assumed to be a normal distribution with the mean and the precision. And the precision is given by the term that you have here. And you have a mean that is given by this slightly more complicated term that you have down here. In both cases, we are performing a sum over the number of data points in our data set. So capital N here indexes the number of data points that we have. And the steps that you'll have to go through in order to derive these updating equations here are more or less what Andrés also showed you earlier today. If you feel a bit adventurous and there's time for it, you can also try to do these derivations here yourself. We have some supporting material for that. So, but depending on how curious you are. And we can do the same exercise here for the bias term, and you end up with expressions here that sort of also bear some resemblances to the ones that we just saw on the previous slides. But for now, we're just going to take these updating equations here for granted and use those as reference for the notebook that we are going to play around with. Yes. So are there any questions at this point to the model or maybe the updating equations? Otherwise, I'll give an introduction to a notebook that we'll be using. Okay. So this notebook here is also available for you. And what I will do now is to just relatively briefly go through the notebook and just give you an overview of the components that the notebook contains. And here we are going to analyze the data set that I introduced just before using this Bayesian linear regression model and do some plotting and try to get a better feel for the Bayesian linear regression model, the updating rules, and what it really means to be Bayesian and all that. When I've done that, the idea is that you are going to continue with the notebook and simply play around with it and updating distributions and visualizing the plots, the results from the analysis that you're going to perform. So I'm not going to go into any details about the individual functions, so this will just be a high-level overview of the main components of the notebook so that you can explore them in a bit more detail in the exercise session that will end at 11:45. So if we just take the table of contents that you can see to the left over here, so we have an introduction to the data set that I introduced before a bit more thoroughly. Then I have something here about linear regression, and not to go through linear regression, but it will sort of help set a reference for your comparison with the Bayesian linear regression that you'll be working with. Then we'll be doing a bit of stuff on Bayesian linear regression, defining a helper routine to calculate elbows. Then there's some stuff about the updating rules and running the variational Bayes inference routine. We'll have another reference solution. So because this model here is very simple and has sort of a nice form, we can also calculate an exact Bayesian solution for our inference problem. So we have that down here, which you can use as reference. And then there's a bit on how to compare the two models that we have using different visualization techniques. We'll be also looking into the posterior predictive that you can use with the model and see how the posterior predictive looks like for both Bayesian model, your variational model, and also what effect it has of changing the parameters that you'll have. And then we'll have a bit of a specification of the exercises that is not so much about you doing programming, but more you exploring the notebook here. And to assist you with this exploration, we have also provided some demonstrations or solutions that sets up a framework for you to manipulate the models and so forth. So if we look at the notebook in a bit more detail, so the data set, as I mentioned, this is about the ruggedness index for African, non-African nations. We'll be interested in these three variables: rugged, continent Africa, which is binary, whether or not it's the nation is in Africa or not, and then the GDP for that particular nation. And here we are loading in the data set. The only thing that I want to point your attention to here is this part where we are dividing up the data set. And this is the type of data division that we are using throughout the notebook. We have our predictor variable X placed in a dictionary that contains two elements. One element for non-African nations, where we have a column vector containing the ruggedness index. And the same thing we have, if we just move a bit to the right, we have it also for African nations. And then we have For the Y part here, we have another dictionary, again, for non-African and African nations containing the log GDP. And the reason why I emphasize that is because throughout the notebook, we are going to separate it out, the data set in these two parts for African and non-African nations, putting all the data in the models into dictionaries of this form here, indexing them with the keys non-African and African. So that sort of is good to keep track of when you go through the notebook. We have 170 countries, and you have a bit of display on the data here. Minor comment, we have a helper function here, prepare figure, which we are going to use extensively throughout the notebook. And this is one of the things that you are also going to play around with. So I just want to point your attention to that this is a function that you can use and also to both plot data and for plotting the models that you develop. And if we plot the data, this is basically the plots that you also saw before. Let me just move this one here. So this is a scatter plot of the data. And here we define, you can expand that on your own. We have another couple of helper functions defined, but that's just helper functions for the exercises later on to assist you with the exploration of the data set. Then we have a bit on linear regression, a bit of introductory text. We have a model specification of our linear regression model. And again, this is standard linear regression. The reason why that we have included this code snippet here is just to show you that for linear regression, we are going to rely on Torch or PyTorch, and this is sort of how one would define the model in PyTorch. So now you can sort of see also the underlying framework on which Pyro that we are going to look at after lunch today on what that is based on. Then we have a bit on training, where we are minimizing the mean squared error in order to get our model. And then we have here, can evaluate the result of the model learning, of the learned model. We have here just called prepare figure that does the plotting for us. And then it returns sort of an axis, sort of where you can use that to hook your model up or the next plot up. And this is why we have defined another helper function, plot model, that allows you to plot this linear regression model that was just returned from the learning function. Yes. And then there's a bit of analysis about the relationship between ruggedness and log GDP, a bit of playing around with what happens if we introduce outliers in the data set, how sensitive is our linear regression model to outliers. Again, this is something that you can explore, also look further into. So these are the results with the examples that we included. The red lines here were the original plots. The green lines are the linear regression plots after introducing a few outliers here and a few outliers here. We have here our Bayesian linear regression model. A bit too large here, but the promised helper routine for calculating the elbow. If you want to go into detail, you can just expand the code on your own. We have the variational solution. Again, we assume a full factorization. We have the updating equations. So these are our implementations of the updating equation for the slope term, where this part of this function here basically implements the updating rule that you saw on the slides. And we have it for the bias term, and again, implementing just the updating rule from the slide. So nothing else going on here. Then we have some functionality for doing the variational base, so doing the variational inference. And the only thing that, again, may be worth to pay attention to is that we have this construct here. We have enumerate X data, and this is just allowing us to pick out the keys for our data set, so African and non-African nations. And then we are doing first an iteration here for African nations, and then we are also doing the same thing here for non-African nations. So we are learning two separate models that are given back to us at the end that we have down here. Oh, sorry. We are learning two separate models and returned by these parameters here. And here we are just calling our variational solution with the data set and our prior parameter settings, and that returns a model here. Again, this model here is a dictionary with one element for each of the two sub data sets. And these are sort of the results that you will see. And again, we have our reporting the elbow, first for non-African nations, then for African nations. And here you can see the evolution of the elbow. It's steadily increasing in both cases, and as it should be. Then there's a bit on model evaluation, where we are generating, extracting sampling from our variational distribution, plotting these sample lines here. And we also have a specification of a base model, the exact base model. And we can do the same exercise again by sampling over the exact base solutions and comparing the plots. This is what we have here. And here you may recognize the same shape of these lines here as Helge pointed out previously, that you have some crossings in these plots here, whereas in the variational solution that we have down here, we see that it's all more cone-shaped. And that's again because that in the variational solution, we assume that our parameters are independent. So the variational distribution factorizes, which is not the case in the exact base solution. And then we have a few, a bit here on our helper function for doing model comparison, density plots. You can play around with visualizations of the marginal distributions for analyzing sort of this basic questions that we posed initially about whether or not we expected to see a negative or positive slopes for the different nations. And then we have a bit here about posterior predictive distributions. So a bit of information on how to do the integration and some functionality for actually doing the plotting, so getting the predictive distribution and plotting the predictive distributions. And this is the stuff that we see here. Also a bit on calculating likelihoods. And that's basically it. So what the intention is now that we'll spend the remaining half hour on is for you to try to go through on your own pace what I just skimmed through here, play around with the different parameters, see what kind of effect it actually has on the model. For instance, if you change the size of the data sets, the helper functions, which I'm going to show you just below, for assisting with that, changing the prior, your confidence in the priors, and so forth. And we have specified some these demonstrations below, where we try to do a bit of analysis here, and it's sort of more intended to be a bit of inspiration for you to play around with. And you can do that on your own. So here there's, for instance, some functionality for extracting subsets of the data, so you can sort of play around with the effect of having very few data points and how does that influence the predicted posterior that we have down here, and how does that influence, for instance, the log likelihood calculations that you can use and do on a different test set. And for those of you who might be more inclined to also play around with a bit of math that Andrés introduced for you, you can also take the optional exercise down here and try to derive the updating rules for W and B. So the updating rules where I showed you the solutions on the slides. In our slide set, we have a bit of supplementary material where we will also do, where you can see the derivations if you want to have a reference. Yeah. So that's sort of sets the scene for the next half hour. We have a question? It should be in the slide set, yes. So it's just after the slides that I presented. So you can see that here, and then we'll have it. So this here should then be just a fun exercise to play around and see the effect of working with this. Any other questions? Okay.